Did you sleep well? All right. Okay, so yesterday I gave a extremely long motivation, right? So we're trying to understand the statistics of the primordial density fluctuations, and I mostly revealed how to quantize the free field in de Sitter space. We went through it. Do we need to be out or? It's a drill. It's a drill. It's a drill. Okay. All right. Okay, back to inflation. So I started sketching what's going to happen once we actually try to quantize at weak coupling the gravitational field in the case of single field inflation, just a benchmark model, just to give you an idea of how these statistics of primordial density fluctuations comes about. So just to try to keep some organization, which I'm sure is going to dissipate with time, I called it item 1.3, inflation. But perhaps before I continue, is there any pending questions, something that didn't sit well with you at night from yesterday? I mean, we were mostly quantizing the free field and reviewing the geometry of de Sitter space and so on, so I hope it was pedagogical. But so this is, this and most of this lecture is still going to be some sort of review, and hopefully then I'll motivate the problem that the Bootstrap tries to tackle in the second lecture. Okay, so for inflation, we're going to discuss in a little bit of detail a benchmark model of single field slow roll inflation. So it's quite minimal. The action is Einstein-Hilbert action and a scalar field whose condensation drives inflation. So it needs a potential to mimic the cosmological constant. So there's some sort of potential. And then there will be some region of the potential over which the expectation value or the classical rolling of the scalar field will be such that there is enough potential energy for it to mimic a cosmological constant and to have some de Sitter-like solution. So it can happen either here or here. So there are various possible initial data for which after you wait a little while, there's some transients, and then you settle into some quasi-de Sitter solution for some time. And this is the region that we're interested in. So the background geometry is some field that has some time-dependent profile and some FLRW metric. So the line element is not going to be exactly de Sitter because there is some kinetic energy for the scalar field, but just for this model, the equations of motion look like this. This is the Friedman equation. There's just the energy conservation. And just a definition. Okay. So if we're going to have some de Sitter-like phase, then it's clear that the kinetic term should be small, because then the Hubble parameter changes very slowly. And then if you look here, if I neglect phi dot squared compared to v, and the v is flat enough, then it's roughly constant, and we get very slowly changing Hubble. Therefore, Hubble dot is very small. So this is what's called the slow roll approximation. And it gives us some computational control for the calculation. So, so let me define some way of like quantifying how slowly rolling you are. So the idea is that you want h to be approximately constant during inflation. And the way to characterize these are so-called slow roll parameters. Epsilon is some dimensionless parameter, and eta, hopefully, this is not going to appear prominently. I'm just reviewing some old stuff. It's not going to appear prominently in the lectures, but not to be confused with conformal time. So not conformal time. And this is, eta is related to the time variation of epsilon itself. And the slow roll approximation is that epsilon and eta much less than 1. Okay? In fact, we usually define the end of inflation when epsilon is order 1. Okay? So just to have some rough estimate of how long inflation lasts, given your favorite potential, then you compute epsilon. When epsilon is order 1, you say inflation ends. This approximation is not good anymore. So the field is close to the bottom of the potential, it's going to start oscillating and so on. You move into another phase. There's a lot of phenomenology here, but it's kind of a textbook material. You can look at Linde's book, or there are many textbooks that cover this, so I'm going to just try to go quickly over this. So this is all I'll say about the background. As for the fluctuations, there is, but it's equivalent to these two. You can get the Klein-Gordon equation for phi, but it's equivalent to the system of equations. All right. Okay, for the fluctuations, if you wish, this is like energy conservation. It's not an Euler-Lagrange equation. It's coming from varying one of the components of the metric. It's the Friedmann equation. But it's all equivalent. You could have written I think if you take a time derivative of this equation here and put this in, then you get the Klein-Gordon equation. That's how it comes about. So for the fluctuations, there I discussed yesterday, there are various gauge choices. In fact, people were very confused back in the 80s about what's gauge invariant or not. I think that the interesting stuff doesn't hide. It can be shifted around by gauge choices and so on. I'm going to describe the gauge in which the resulting fluctuations are closest to the physical observables. Okay. Now they also have some nice properties that they have soft limits, and at the long wavelength limits, the fluctuations freeze out, so they don't, feel the expansion of space-time once they have long enough wavelengths. So they have all sorts of nice properties. So you can choose other gauges. They're useful for highlighting different parts of the computation, but let's focus on one specific choice. So when you're looking for fluctuations, you could have written phi as the background solution plus some small fluctuation, which we're going to set to 0. So this is a gauge choice. So in fact, phi bar, it will be time dependent and it will foliate space-time. Okay? So the value of phi acts as a clock, because phi bar changes with time, so it naturally foliates space-time. So phi bar 1, phi bar 2, etc. So often this is called the clock field. In fact, you'll see in the literature single clock inflation also. So this is for phi, and then there's the metric, and the metric will have you will eat up this scalar fluctuation in a variable that I call zeta and the gravitational field. So I described this yesterday, but it was too telegraphic, so let me just repeat it. Sorry. So the metric in ADM form, Arnold, Deser, Meissner, so they were the ones that figured out the Hamiltonian form of Einstein's equations. Is written like this. So the physical degrees of freedom are encoded in the metric on the 3 slice. So in this cartoon, you have the foliations. Then you have like little clocks here. So when you compare the ticking of your clock and point A to like the equivalent point A, t plus delta t later, you'll see that there is a little lapse. The clocks are slightly mismatched, other than just adding delta t, and this mismatch is controlled by the value of the field n, of the variable n. Okay, so when you compare the clocks, it's controlled, so it's called lapse. And also, if you put some little rods here, maybe you just stare at the formula, you don't care about this physical picture. But when I learned this, I was confused, and I read in the textbook of Meissner, Thorne, Wheeler some explanation for this, and I thought it was useful. So now when you compare, then you'll see that the coordinate system is a little bit tilted, and the way that the coordinate system is tilted is characterized by these vectors ni. So it's shifted. Okay, so it's the lapse and the shift at a given point. But they are Lagrange multipliers. So n. So there is no. So the Lagrangian contains no n dot or ni dot. So they are Lagrange multipliers. Therefore, you can integrate them out. So the delta S, delta N equals 0, delta S, delta Ni equals 0 are constraints. So this is called the momentum constraint. This is called the Hamiltonian constraint. And people make a big deal out of this because there is no Hamiltonian in general relativity. It means that the Hamiltonian is 0. And if you try to quantize it will be a function of the fields phi and hij and its derivatives, so it's conjugate momenta. If you try to quantize, promote h dots to delta hij, you get something that is known as the Wheeler-DeWitt equation, okay? But it's just canonical quantization of this theory in the Schrödinger picture. All right. So just to say that these are constraints, they are actually not trivial to solve. This one you can invert, you can solve exactly, put it back in the Lagrangian, but this is a differential equation, so you have to solve perturbatively. Okay.
In what sense is 5 bar a clock? Its value can go back and forth, right?
During inflation, we assume that it's a good clock because it's rolling downhill, so its value is changing smoothly, monotonically with time. Yeah, if it's doing something like this, then it's not good as a clock. But for inflation, it provides a natural foliation of space-time. I mean, even if it's doing something like this for a neighborhood for some time domain, it's okay, but then you run into issues with caustics and stuff like that. So, but for inflation, it's good enough. In fact, we don't see any of this background stuff. Again, the whole thing about inflation is encoded in the fluctuation. So this is a cartoon of how we think things go about. And okay, so then your task to quantize the theory is to solve these equations and write an, I forgot to, so Hij is A squared delta Ij, the usual background solution, plus 2 zeta delta Ij plus gamma Ij with gamma II. So again, this is a 3 by 3 matrix. It's symmetric, traceless, transverse, so there are only 2 degrees of freedom. So this is the graviton, and this is the scalar fluctuation that got eaten like a la Higgs into the metric. So if phi bar doesn't have time dependence, then you can't do that. It's like there's no unitary gauge unless you have spontaneous symmetry breaking in the Higgs mechanism, right? You can't, at the top of the hat, have the gauge fields with longitudinal mode. So same thing here. This zeta variable is only well defined as long as the field phi has some time dependence. And we'll see that come about like immediately. So then your task is, in order to quantize, is to put this back in and solve the constraint equations. It's not trivial, and here's the result. So quadratic actions. I'm probably missing numerical factors. I thought that there's a 1/8 here, but the important thing is the epsilon versus m Planck here. Okay. By the way, you see that if h dot is 0, if it's exactly the Sitter space, then this action blows up, right? Meaning that the scalar field has no time-dependent profile, and therefore you can't Higgs, you can't eat the scalar fluctuation into the metric. So that's why you should have expected the action, something special to happen if I take the de Sitter limits. And now you notice that we have a quasi-de Sitter space-time, and this looks like the action of a free field. You could have even anticipated that they will be massless fields, because if I try to shift them, you can absorb the shift by change of coordinates. So you can't generate a mass term. Yeah?
Could you explain again what you were doing to Higgs, this delta phi? What is it?
It's a choice of clock, right? So there is only one degree of freedom in the fluctuation of delta phi. So you choose the clock or the time variable in such a way that surfaces of constant time match surfaces of constant phi bar. So therefore, it can't fluctuate. But then the scalar degree of freedom needs to reappear somewhere. And then it appears here. If you try to do a change of coordinates to get rid of zeta, then you will see that zeta is minus, I think, something like this. Yeah, I think something like this. So you see that if phi bar has no time-dependent profile, then you can't access this gauge. Okay. Yeah.
Are we just, do we have to set the normal volume form for those actions? Or?
I think I put in all the, I think, So here, these gamma ij's are contracted to the Euclidean matrix, so it's really just like two massless scalars, pretty much. But then the covariant derivatives are contracted to the background matrix, so they looks like the action of a free field in de Sitter or quasi de Sitter. Okay. Yeah. This is a short exercise. If you want to start from the gauge in which delta phi is non-zero and then zeta is 0, you can do a change of coordinates, a time reparametrization to remove. Well, we can do it. I mean, say this is a parenthesis, okay? Phi equals phi bar of t plus reparametrization plus delta phi. We want to remove delta phi. So then it's phi bar t plus t phi bar dot plus delta phi. So you want this to be 0. So t is minus delta phi over phi bar dot. Now the original metric now there's no scalar degree of freedom in the original metric. So well, this is schematic. Okay. If I put now a squared of it's a squared of t plus t because you changed coordinates. Now if you expand this out and plug this in, then you'll see that you will automatically induce scalar fluctuation, right? So a of t plus t, a of t plus a dot t, but a dot is Hubble a t, right? And big T is delta phi over so when you plug this here, then and expand to linear order, you see that you induce zeta, and that's where it comes from. Okay. If you don't sweat it. It's a technicality, but just to show that at linear order it's very simple. At second order it's already a huge mess to do this because the graviton doesn't mix with the scalar at linear order in perturbation theory. So I'm erasing it quickly so you don't copy it, because I'm hoping that we'll move on from this. So it's like a massless field in de Sitter, but the important thing is that if you try to go to canonical normalization, they have different coefficients up front. Therefore, the 2-point functions will be different. So the 2-point function of zeta will be, let me try to copy it so I don't, h over m Planck squared 1 over 2 epsilon. And this is what's measured. And I'm putting a k cubed here. Remember that it's 1 over k cubed. The 2-point function of a massless field. right? So this is what's measured. And again, I quote the number. And we would like to measure this, which right now we parameterize as some small number times AS because we haven't measured it yet. And we know from data that R is less than, I think, 0.05. I don't remember the current bound. But this is experimental, okay? So we haven't measured this, but we have a bound. Now, where is the scale dependence? The scale dependence comes in because these h and epsilon are not constants. So they have some mild time dependence. So it really depends on there is some very small k dependence, and you can read off the tilt from doing that. So it's not really true that they go like 1 over k cubed because h and epsilon depend on time. Okay. So there is a way to approximate the calculation. If you remember, let's look at the classical mode function of a scalar field, of a massless scalar. So if I look at the classical mode function of a massless scalar, it looked something like this, some h up front, maybe 2k cubed, if it's canonically normalized. Then the point is that there's something like this, 1 plus I k eta. So you see that as eta goes to 0, if I go to late times, then this goes to a constant, which is the story of the freeze outs. There's this competition between dilution and growth. But you see that things turn around. As eta goes to minus infinity, it's highly oscillatory. So as eta goes to 1 over k, it starts to freeze out. So the transition between oscillations and freezing happens as k eta is order 1. And this is a physical scale associated to the mode. It means that the physical wavelength of the particle is comparable to the de Sitter radius, the inverse Hubble length. So the word that you will see cosmologists referring to all the time is that the mode freezes. So it's the freeze out. Freeze out, or the mode goes super horizon. Just some terminology. So this is crucial. If we're going to go the holographic routes, this intuition is very important. It means that for a given wavelength, the physics is dominated by a given time. So for every given wavelength, when conformal time is order 1 over k, that's where most of the interesting physics happens. That's when the burst of particle production happens for the given mode. There is some fast transition between oscillatory behavior and frozen fluctuations. Okay, it's just at short distances the mode is highly oscillatory, gets stretched. Then when it hits the Hubble horizon, it's like pumped. You get like some condensate, and the condensate very quickly settles. So that's the idea. Okay. So this intuition will play an important role when we go beyond the 2-point function. So that's why I'm emphasizing it now. Therefore, if I want to understand how this thing depends on k, I should evaluate h and epsilon at the points at the instant in time when k eta is order 1. Okay, so that's why each mode each mode is experiencing a slightly different value of Hubble. So if I draw again this picture of the scalar field and its potential, so the inflation, as inflation goes on, the scalar field is rolling. So there's like a value phi 1 is one of the times, eta 1, phi 1, which is related to some eta 1. And then later on here, there's some phi 2, which is related to some eta 2. If I draw the picture of inflation going on, this is the end of inflation. Let's say inflation ends here, okay? And then this is eta 2. This is eta 1. So then at eta 1, there will be a particular wavelength that is produced very efficiently and leaves a non-trivial two-point function. So these guys here, they will have fluctuations of order h at eta 1 squared, okay? Now, these guys here, phi 2, let me try to make the color scheme consistent. So, this is phi 1, this is phi 2, and in white it's the end of inflation. So, then at phi 2, at eta 2, there will be other modes that are produced. It's almost scale invariant, but the Hubble rates that they experience is slightly different. So, you see, because the potential energy changed a bit from here to here. So that's why there is scale dependence, at least in this picture of single field inflation. Is that clear? Okay. So that's how you compute the tilt. So let me just tell you the result. So we write, for historical reasons, we write that it's really k cubed minus ns minus 1. Yeah. It's a small number, but for some reason we write this number close to 1 minus 1. Don't ask me why. Minus nt. For the tensors, we knew better by the time we understood tensors, so we write it as nt. So ns minus 1, and now you'll see why I had to introduce two slow roll parameters. So ns minus 1 turns out to be minus 2 epsilon minus eta, while nt is minus 2 epsilon. So that's why you have wiggle room to play with these numbers, because you have two scales, epsilon and eta, that measure these two numbers. And this one we have already pinned from data. So from Planck, this is 0.96 minus 1 plus or minus. So if you are like a naturalness type of person, you think everything should be comparable. Epsilon and eta should be comparable. Therefore, it gives you a proxy that epsilon should be order 10 to the minus 2. And look at the current experimental bound. So that's why people are like, we're there, we're almost there, we're almost there. But you know, you could just as well make this tiny and put most of the contribution on this parameter here. Or you could cook up a model in which you introduce a new scale and you differentiate. So that's why in the first lecture, if you remember, I drew this picture of the energy scales, and then I said there's some blurry various scales that determine this guy here. So in this case, it's epsilon eta. So we still don't have enough data to tell them apart. But you can do a little exercise at home. You already discovered something interesting. If inflation is like power law, not exponential expansion, and it's single field, then you will conclude that it's ruled out. Because it's a very small calculation, you'll find that eta is 0. Therefore, you will make a prediction that ns minus 1 and nt should be the same. So it's ruled out because we already have a bound Yeah, maybe it's in tension, but it's 1 sigma ruled out. Okay. The other thing is that if we measure R, then H is not incredibly far from M Planck, which I emphasized in the first lecture. So this is a huge opportunity, right? So can we do particle physics close to the Planck scale? And maybe nature has given us this opportunity. Well, that's great. So this is the end of what I had planned for the first lecture. Here we are. And I'm going to move on beyond the 2-point function. So there are any questions about the 2-point function? So let's move on. Non-Gaussianity. All right. So what is non-Gaussianity? It's it's a process that is not Gaussian, which means the 2-point function is not the only statistically interesting quantity. So a Gaussian process is such that all odd moments are 0 and all even moments are given by sums of products of the 2-point function. While anything non-Gaussian will have different statistical properties. So the first thing you should look at is the 3-point function. So the simple diagnostics. Non-zero 3-point function, or we call connected. It just means you take the 4-point function and you subtract the weak contractions. Okay? All right. Of course, once you go to non-Gaussianity, anything goes, but in a weakly coupled theory, we expect the dominant contribution to non-Gaussianity to come from non-zero 3 and 4-point functions. Just think of weakly coupled theory, you just draw Feynman diagrams, and you have scattering. So you have 2-to-2 scattering or 3-point scattering. So that's already a non-Gaussian correction to free propagation. Okay, so that's pretty much it.
Are you computing the correlation functions or like the analogs of amplitudes?
The correlation functions are the analogs of amplitudes. Because in amplitudes, let me contrast. In amplitudes, you have, you send something in, and then you collect stuff out. Of course, if you're willing to, so this is physically what happens. If you're willing to analytically continue and talk about negative energies, you could imagine having some outgoing and ingoing stuff. This doesn't make physical sense, but the mathematical formula makes physical sense, and this is closer to what we are doing here. So here we only control the initial states. We say that it's a vacuum. And then at late times, you have some non-trivial correlations among the modes. If there is non-trivial correlation, at some point there must have been interactions. So there's some process here. Out of the vacuum pops like some interaction, vacuum fluctuations. They interact, and then they're stretched by the expansion of space-time. So this is what we are. I'm going to contrast two different ways of doing the computation, but they encode the same physics, the physics of interactions.
So is the claim that those two actions need to be modified with the quadratic actions?
That's right. So that's just the quadratic approximation, and the natural thing to do is to go beyond the quadratic approximation. And then I'll sketch to you what happens in this case, which turns out to be extremely complicated calculation that was heroically done by Maldacena in 2002. And, but then you clearly see that the method runs out of steam. Okay, for 15 years people pushed this and tried to do more and more complicated calculations. And for example, let me describe the calculation. I mean, not just jump too far ahead. But you compute very simple things and you see that like very simple diagrams, for example, using bulk perturbation theory took people like 3 years to sort out what exactly happens and so on. So it seems to be asking for a better method. This is where this whole idea of the bootstrap will come in.
You mean gravitational aptitude? Like graviton diagrams?
Yeah, sure. It can be, even in rigid de Sitter space, it's hard. Yeah. But you can do, yeah, the first calculation was actually done in single field inflation. So it's, there is small gravitational back reaction. But it's simple enough that it can be done, but extremely hard nonetheless. So I'll tell you how it works. So this, I want to describe the phenomenology. So I'll draw lots of pictures and explain what you should be able to tell from these measurements of non-Gaussianity. So the first part will be phenomenology. So up to now, we mostly described this diagram for the scalar field and for the graviton, the two-point function. And now what happens if we, for example, measure a three-point function of a scalar? What kind of physics can give rise to the three-point function? And I'm going to assume that we are at weak coupling. So we can use bulk perturbation theory. So this, the idea is that this is some sort of a collision process, and you can think of measuring this three-point function as some sort of collider experiments. Just like you scatter beams off of the LHC and you measure the resulting debris, there is some type of interaction that creates cosmological correlations, and you look at the sky, you look at different distances in the sky, and you try to reconstruct the process here. So then it's what people call the cosmological collider. So the name was proposed by Akani Hamed and Maldacena. The idea was floating around already for quite a few years, but they made it explicit and added a few new things. So now I'd say it's a popular name. People like it, so that I mention it. And it's a very good qualitative analogy that turns out to be quantitatively correct also. So let's consider a diagram at weak coupling. So one possibility is the following. There is a new state that mediates some non-trivial interaction between the three scalar fluctuations. Okay? So let's look at this diagram. So first of all, there is linear mixing. So this is not allowed in maximally symmetric spacetimes, right? Why don't we draw linear mixing diagrams all the time in Feynman perturbation theory? Because in flat space, you can always change bases and remove linear mixing. But we are in a time-dependent cosmology, in inflation, so that's allowed. Now, this is a new field, let's call it sigma. And these are the density fluctuations, the ones that we actually measure. So the question is, what is the form of the 3-point function that will allow us to do spectroscopy of this new particle? So that's the idea. We want to understand the physics of inflation. Inflation maybe happened very close to the Planck scale. So can we do spectroscopy at those enormous energy scales? Maybe we detect new states, and then we can incorporate them into our understanding of nature, figure out what inflation was made of, and so on. Just like when you scatter fermions or pions at the LHC, you discover new states, W bosons and all sorts of amazing stuff, and you incorporate it into your understanding of the universe. So same story here. So first thing to remember is that, you know, there will be two scales now. There will be eta 1 and eta 2. And this diagram will be dominated by, so this is the mode K1, this is the mode K2, mode K3. This will be dominated by K1 eta 1 order 1 and K2 or K3 eta 1 order, sorry, eta 2 order 1. Okay? So that's the, so these are the two times that play the most important role given K1, K2, and K3. Okay? So in this case, I would have a triangle that looks something like this. K1, K2, and K3. This guy has a short, he has short length, therefore the wavelength is large because it's wave number. The wavelength is large, therefore it was sourced earlier during inflation. Okay. While these guys have big wave numbers, small wavelengths, they were sourced later during inflation. Okay. Therefore, in this configuration, the imprint of the new particle should be very clean because you give it a lot of time to travel through the space-time, and it should leave an imprint in the form of its 2-point function. So that's why we were spending all this time quantizing the massive field in the Sitter space, because even though we only observe the massless particles at late times, we have a chance to observe the 2-point function of massive particles. Yes?
Sorry, I think I just missed what you said. Are you here in this case assuming that K1 is very small compared to K2 and K3?
Yeah, you can compute the 3-point function or look at the 3-point function in any configuration, but in this limit when K1 is much less than K2 and K3, then you can cleanly separate these two timescales, and it should be very obvious what the 2-point function of the new state is. There is another limit in which the K's are all comparable, but then everything is produced at the same time. It's hard to distinguish a new state versus just self-interactions. Okay, so this is just to contrast. Let's see. So there are two limits. One is the equilateral triangle, K1, K2, and K3. Of course, you can compute at any triangle, but just to give an intuition, in momentum space, you need to have the momenta adding up to 0 because of translation invariance, okay? That's why I'm drawing these triangles. These are triangles in momentum space versus the K1, K2, and K3. So in these limits, then you have this clean separation between the modes. while in this limit, everything is produced at the same time, so you're mostly, it's like as if you integrated out the heavy physics and you're looking at self-interactions. So they're both important. So this, so first conclusion of just drawing these pictures without doing any calculation is that if it,
I have a question. Regarding these 3-point functions, so these zetas are curvature perturbations, right? So 3-point functions, I'm just wondering about this K1 being the inverse wavelength being larger in early stage of inflation. So basically you have, in the initial stages you have slow roll, but somehow this, for the scalar you have to do this Higgs mechanism that we were talking about in terms of understanding this curvature perturbations, right? That's why in the early stages of inflation you have, for the zetas, you have this inverse lambda 1 to be very large because it's very low change in energy.
yes. Sorry, what's the, maybe I missed the question, so, or you're just trying to explain?
Trying to understand in terms of this Higgs mechanism.
No. For the whole diagram, okay, so the idea is that the physics is dominated by just a couple of instants in time, and then things freeze out. And then inflation stops, and there's no Higgs mechanism anymore. But these remain frozen until the physical wavelength of these fluctuations becomes comparable to the size of the universe. So this is like some fossil that is frozen, and then later on in the history of the universe, the size of our horizon starts growing, and then it becomes comparable to these fossils that were frozen for a very long time, and then they start undergoing gravitational collapse. Okay, so while the fluctuations are set up, we are always in the Higgs phase. And then there's a beautiful theorem of Weinberg that says that doesn't matter what happens later on, these remain frozen for a very long time and reconnects to our usual description of the universe. So for everything that I'm drawing here, we're always in the Higgs phase. We can always talk about zeta. In fact, we can even forget about this whole Higgsing and blah, 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 and think of these are almost massless fields in de Sitter space. It will give an exquisite approximation to the diagram. It will capture all the physics. Just one point that I want to make. Without doing any calculation, you see that if you draw irrelevant interactions, just self-interactions of zeta or the clock field, if they're local, then the signal always peaks in the equilateral configuration without doing any calculation. Why? Because if I start to create some hierarchy between the momenta, it means that one of the modes wants to be produced copiously earlier than the others, but you only have local dynamics. So there's a tension. And of course, there's quantum mechanics. You can integrate the vertex all over space-time. So it's not like it's not a delta function and the equilateral configuration vanishes. But it gives you intuition for why self-interactions always peak around the equilateral limits, and then as I squeeze, they decay fast. So the rate of decay is crucial in this business, because depending on the rate of decay, you have a better fighting chance of measuring it in the data. So typically what, yeah.
So you said you could also measure this in the de Sitter background with a good accuracy. Do you have enough de Sitter isometries to fix the 3-point function?
Yes. Yes. If it's pure de Sitter, it's unique. It's just self-interaction, just phi cubed. From looking at this diagram, there's clearly something missing, right? So let's do this. Let's take a soft limit of a 4-point function in de Sitter space. Now it's a standard 2-to-2 type of a correlator with an exchange, and that's a key observation actually made by Sandeep Trivedi And it's a paper of four authors. Sanjeev Trivedi was one of them. They pointed out that a lot of the correlators that are computed in inflation are really you can forget about inflation, do a computation in de Sitter space, but of a 4-point function, and then take the soft limit of the 4-point function. Okay? So now what's going on? This guy here is very soft, so it has very long wavelength. It redshifts away very slowly. So the three other modes, they don't feel like they're in the Sitter space anymore. They're in some very mildly time-changing cosmology. So it mimics the effect of inflation, and it gives the inflationary 3-point function on the nose. So the richness of inflationary 3-point functions is coming from the richness of the Sitter 4-point functions. Okay? So that's an important point. Okay. So let me erase this. I'm going to continue just discussing the phenomenology of the 3-point function, but maybe, okay. Before going for the break, I just want to emphasize that here we probe self-interactions. While here we really probe particle production. So if there are strong self-interactions, the signal always peaks around the equilateral configuration. And if we go to the squeezed configuration, we should see imprints of new particles. So if you open any paper about non-Gaussianity, it says there is a type of local of non-Gaussianity that diagnoses a signal around the squeeze limit. It's called, for historical reasons, the local shape. It's the most non-local thing you can have during inflation. But it's called the local shape. And it says it's a diagnosis of multi-field inflation because you will detect new states if you see anything there. It's a prediction that if it is inflation with self-interactions, you can never see anything around the squeeze limit. I'll quantify it. Of course, there is some signal there, but it decays too quickly. I'll quantify what I mean when we're back from the break. So let's stop here for now.